pump water up to a level 4 meters above the top of the hemisphere, so 4 meters above what would be the center. And what I'm trying to show you here with the maple is what we were talking about Friday, that there are two ways you can do this. You could take the y positive down, or you can measure the y up from the bottom, so that y, or measure it up from an origin at the center of the basin, so that y is positive up and negative down. So if you want maple to print the integral the way it would appear in the book, so that you see the problem set up without actually getting the answer, you type INT with a capital I, which you notice I've done. And you remember, if you were here, this is a problem with metric units, and the density then for the water is 9,800. Then for pi in maple, you either have to spell it capital P-I, or else you have to use the mouse, and you can go, you can find the Greek letters and you can click on one of them and enter it that way. And so 9,800 pi, then the 4 minus y square is the radius from the vertical axis of your basin, which has radius 5 because it's a hemisphere, no matter where you are. And then the 4 minus y would be the lift if your y is positive up, so that your lift is the absolute value of y to the ground level, and the absolute value when y is negative is minus y. And then the reason for the 4, again, if you were here last week and remember, the problem is that you were lifted 4 more meters above where the center of the bowl would be, up to a height of 4 meters above the ground. Okay, so then you could retype the problem using small letter I, and it'll give you the answer, which is number 2. Or if you typed it with the capital letter, as I did, then you can type value, and then percent refers to what the computer executed on the previous command, like ditto marks would be. Maple doesn't use ditto marks as you do in English, because they use the ditto marks to begin and end a string if you're writing a program. So anyway, you use the percent sign. So there's an answer. Then if you do it over again, line 3, so I've done the setup again, the INT, and the same density in pi, and the same radius. 4 plus y, if y is positive down, is measured from an origin up at the center of the basin. And you notice this time the limits are 0 to 5. You always want the limits on your integral so that your y is increasing from what you have at the bottom to what you have at the top. Notice on line 1, your y was increasing from minus 5 up to 0. So you have to do that so that the dy is positive. And again, if you ask for the value, number 4 is certainly the same as number 2. So this is proof that you can do these things either way. You get maple enlisted so you get to your answer without doing so much labor, so you can compare them. Then what I did was to draw a picture of a portion of our basin, And you see, really, you have a three-dimensional situation because you have this bowl. And so if you wanted to plot this, if you want to draw it, you bring up a program called plots if you want to draw graphs. And then you have two ways you can do it. When it's when you're, whatever you're trying to draw, if it's a curve or a surface, whatever it is, it can either be defined as a function or it can be defined by an equation. If you define by an equation, then you type implicit plot. And if it's three-dimensional, which a basin is after all, then it's 3D, you see. So implicit plot 3D. And then you type the equation. So this would be the equation for part of a sphere, which is what you have. And if it's a sphere in three-dimensional space with radius 5, then the equation is x squared plus y squared plus z squared equals radius squared. So you see where I get that. And then I'm thinking of x coming out from, I'm thinking of the origin in this picture as back down in the corner of the box behind the portion of the surface, so you don't really see the origin. The x-axis is coming outward, and the y-axis is going off to the right and z upward. So then to get my portion, what I have, you see, is actually a quarter of the surface of this hemispherical bowl. I go 0 to 5 with x and 0 to 5 with y, and then minus 5 up to 0 for z. And so my origin is in the back corner of the box up at the top there. And the other way you can do this, instead of defining your surface as an equation, you can define it using function. So if you're doing that, you do plot 3D, and then the brackets indicate what we would learn to call a vector in third semester calculus. Three-dimensional calculus is really math 275, so if you want to draw the picture, you have to admit go that way. So then you have x, y, and then your function of x, y. And you have basically the same picture. So let's just do a little more on this. Going to be second 21 that we talked about on the Friday. So now we'll continue on with the 6.5, and that's 5 and 6.6, which we'll work with more tomorrow. So the next problem in 6.5 is number 23, and what it wants us to do is to show that the work done by a force is applied to a moving object when the object has mass m is the change in what we call kinetic energy. Kinetic energy, Newton defined kinetic energy as half the mass times the squared speed. So supposing that we have a constant mass, which is what I'm doing here with this derivation, then according to Sir Isaac's law, the force, which in general is the time derivative of momentum, so that allows that mass could change as well as velocity. If it's a constant mass, then it becomes mass times the time derivative of velocity, which is what you call acceleration. So then what you do to do this proof is you rewrite your differential quotient here by putting in, dividing by, and multiplying by another differential, dx. So that's legal math because these would cancel and you get back to there. And then also, if x of t is your displacement, so you have, say, something moving along a track like this, you have an origin here, then measured, then as this moves, measured from the origin from here to there is what you call displacement in physics. So if that's x, then dx dt is your velocity. Velocity is really a physics idea. There is a magnitude which you call speed, and there is a sense, there's a line on which this acts, so there's a sense of direction. So it's what you really call a vector quantity. We talk about vectors in chapter 12, the start of Math 275. Unfortunately, the way that we teach calculus, we don't really work with vectors until third semester, but if you're taking physics or engineering fundamentals, you're working with vectors already. So I would be the first to agree that we really don't quite do it right, but unfortunately, it's not up to me. Anyway, back to here. This is velocity then, and this is repeated. So our force then now is written as a function of x, if you multiply by the mass. Here you see your function, your force function is mass times a function really of t, and with the game here with the differentials, we've rewritten it as a function of x if you have mass and then replace the dv dt with v dv dx. So then if you want to integrate this between limits on x, the idea being that your velocity would change from one position to the other, and so your kinetic energy would, then you'd have mv dv dx, that's your force, and then this dx is this one. And then you could cancel those, you see, and integrate with respect to v. Okay, so treating m like a constant, the integral of v dv is a half v squared, and then you're evaluating between the x where you start and the x where you finish. If you moved something and changed its kinetic energy. So you have the difference in what Newton defined as kinetic energy, which is a half mass times speed squared. So this proves a principle that you use in the physics class. So problems 24 and 25 apply this, as I'll show you with 24. What this recipe does is let you solve problems quite easily that would be pretty hard going otherwise. If you look at problem 24 in your book, and if you're doing my math lab, there's equivalent things there to the ones in the book. The question is how much work to make a 2-ounce ball, this would be like a ball for playing table tennis, go 160 feet per second, which is pretty fast. Okay, so what you want to do is use this idea that it's starting out not moving. So your V1 would be 0, and your V2 would be the 160 feet per second. So what the work would be then is really whatever you get out of a half, the mass, and the speed square for this mass and that speed. The thing you have to do is you have to get your units straight. This is always where people get in trouble with physics, chemistry, engineering. You got to keep the units straight. And so, first of all, with mass, if you're using English units, which you are because this is ounces, your mass is your weight in pounds divided by whatever is the correct acceleration for gravity, which is not exactly 32, but close. So to get the answer in the book, you'd use 32. Okay, so there's 16 ounces in a pound, so 2 ounces is 1/8 of a pound, and you divide that by 32. So that goes there. So your work done is a half the kinetic energy at the final speed minus the kinetic energy at the start, which would be speed 0. And so then your V in feet per second would be 160. And you see it's squared. And then you can do some canceling, because with the 30, first of all, with this, you see you have 1/8 times 32. And I wrote the 32 as 8 times 4, and I can cancel each 8 into each 160. So I have 20 times 20, and I have 2 times 4, and so I get 50 foot-pounds. So with the formula, these are not that hard to do. 25 is similar to this. Okay, another type of problem we have is force at a constant depth in a fluid when you know the density of the fluid, which could be air actually, or it could be water, or it could be something else. It could be liquid chocolate, say, or it could be oil or whatever. The only difference in the problem is what's the density, really. So we use Greek letter rho, and Pascal was a French mathematician and physicist, and did a lot of things in the development, the early development of calculus. He didn't have calculus as we know it, which goes to Newton and Leibniz, but he certainly was working with some of the ideas, and that in turn is what helped develop calculus later. And he did a lot of work in probability and that type of mathematics, and also in physics, the Pascal law in physics. First of all, you define pressure as force over area. Like, for example, in English units, air pressure is approximately the 14.7 psi, pounds per square inch, and so on.
Atmospheric, you mean?
Yeah, atmospheric pressure, yeah. And so that's using pressure as force, pounds per unit area per square inch. And So pressure then, this is Pascal's law. If you're at a depth h in a fluid, whether it's air or water or whatever, pressure is the density that's appropriate for whatever it is, times the depth from the free surface of the fluid. So the force against a differential area, so you have a triangle like in these problems, and you have, for example, water on one side. This could be, for example, the side of a tank that has water in it, and you might have a window that's been made in the wall of the tank so you can look in and watch the fish or something like that. And so if you're at a depth from a free surface to a slice across the window area, then according to this, the pressure would be density times the depth from the free surface down, and then the force would be the density times the depth times the differential area, so the area of the slice. So that's what I've written here. dF is pressure, then dA. So if you look at problem 33, it refers to an example that's in the book, except that in 33 they've changed where the origin is. But what it is then is there's this triangle, and you have measured from here down a distance of 5, also 5 this way and 5 that way. So if you're taking your origin there on the free surface, you would have a way to get the equation of this edge of the triangle, and therefore to get x, and therefore to get 2x, where 2x dy would be the area in blue. So the edge of your triangle is this line from 0 minus 5 over to 5, 0. So you can get the equation because you know, you can see that the slope is 1 because your rise, say you're going from here to there, your rise is 5, and going sideways, your run is 5. So your slope is 1, and your equation is y equals slope times x plus the y-intercept, which is at minus 5, if your origin's there. So then you can say x, solve this, x is y plus 5. So your differential area is the area of your slice, which is twice x dy. And then this says your variable is y. If you're going to do an integral, you have to write things in terms of y. So you use x equals y plus 5. So your force against your differential slice, then, is your differential force. So it's density and the depth, 2y. Okay, so if you're measuring from here, then again, going down, your y is negative, so you need the absolute value for your depth. This is much the same situation as we were talking about at the start of class with this problem here, where we were talking about the hemispherical tank and measuring from the center of the hemisphere. If you're measuring in such a way that the y is negative as you go down, then you're going to need the absolute value for your lift. So we have the absolute value for our depth, then the 2 times y plus 5 is the 2x is the length this way, and then the dy is the width that way. So the force against this region then is between y equals minus 5 and y equals, not clear up to here, they want the force against the part from minus 5 up to minus 2. That's because of the way the problem is worded. So it isn't the whole thing clear up to the surface. And so your limits then are minus 5 to minus 2. Density, depth, which is minus y because that's your absolute value. Your width, and dy times the width makes the area. So you could take the 2 out and double, and then you'd have minus 5y minus y squared, and this is a basic sort of integral, and put in your numbers and you get this answer. This is the same answer that's in example 6 in the book, which was this same region from 5 down up to 2 down from the origin. In the example in the book, they took the origin in a different way. And then problem 34 is the same plate again, but again, it's has the origin at the top of the triangle, and the triangle of water rather than up here at the free surface. In other words, this origin, compared to this one, is 2 feet down, so it would be as if it's there if you were in this picture. So this then is a picture of the triangle that, in this example, doing it this way, goes from my stick on down. So you can take the origin there at the top of the figure where you want to work, and you'll see that you end up with the same thing. So I've got some people who've arrived. Give the first handout by the answer that's here. So then if you put all this together, you end up with the book's answer. Now I'm about to show you an easier way to do a problem like this. So this thing doesn't have to be as bad as it appears. As far as doing the homework, certainly use the integral table, and then you can do like this. And there's a similar thing in the My Math Lab where your integral table will give you what you need if you're doing things that way. So what you can do with a problem of this sort is to use what we call the centroid concept. And we'll go on with that in just a second. And if you'll notice, I end up with the same answer here that I have here. This is more the way an engineer would do this sort of thing if it were a practical problem. I want to get my sign-up sheet. If you have uniform material, or if you are thinking of just a plain area as a geometric figure, and you want the geometric center of the plane area, the coordinates are the balance point for such a thing, and you write x bar and y bar. So let me show you what I mean here. here's some homework papers. Paper is quite uniform. So if you have a geometric figure or a figure made of uniform material that's like a plane, then your balance point will be on every line of symmetry. So for a rectangle like this, you'd have a center line this way and one this way. And so approximately where the center lines would cross, you see you have your balance point. Now I'm cheating, right? Everybody sees I'm cheating, because the true balance point would be if this were a needle and it would balance on the needle. And you see I'm cheating because I am using the end of the pen, but that's the idea. So what you want then is to get this balance point. This is what we call the centroid. If you have a semicircle like this problem, and the radius is A, you can prove then that, you see, you have a symmetric figure on either side of the vertical axis. And I was just saying that your centroid will be on every line of symmetry. So it would be on this axis at some point up in here, a distance rho, this is the Greek letter rho again, from the x-axis. And what we're starting in section 6.6, and we'll continue with tomorrow, is how you use integrals to identify the, in this case, what number would be the rho. Well, it turns out that for a problem like that, if the radius is A, the x bar is 0, and the rho measured from the x-axis is 4 times the radius over 3 times pi. Now, I'm not going to prove that today, but if you use that, you can get at a problem like this one. Because it turns out then that the force against your geometric figure will be the density, the depth from the free surface to the centroid of your figure. So if it's rho in red up to here, then if this is 6 down to here, the depth from the free surface is 6 minus rho times the area. And you can get the area easily because it's half of pi times the squared radius. So the depth then from the surface to the rho, which is 4a over 3 pi, is 6 minus that. And then if you get a common denominator, you see you have 18 pi minus 20 over 3 pi. So your force is 62.4. 18 pi minus 20 over 3 pi, and then your area, and the pi's cancel. You work this out, you'll get the same answer this is, and it's a whole lot easier. So what people do if they're working a practical problem of this sort is either they go to an engineering handbook where there's drawings of all kinds of geometric figures that anybody might have, and where it shows what the coordinates are of the centroid, or else you could go to the internet and find a site there where you could get it. So typically, most of the time, people are not really going to work the integral out like this, but the difference between training and education is if it's education, at least you've gone through this so you understand where you get the coordinates of the centroid. So training, you just say, well, this is what you do. And so my effort is education, of course. Okay, so using this principle that it's density times depth of centroid times the area is certainly the handy way to do these problems if you have a way to look up where the centroid would be. While I'm thinking about it, let me give these papers back and then we'll go on. It's not here. Okay, so now let's finish today, and this is the start on what we'll work on tomorrow, section 6.6, with density variable. Say this is the Greek letter delta. We have that mass, first of all, would be the integral from between your limits on your region of density dA. Okay, so if your top curve is f of x and your bottom is g of x, then it would be density, and then your differential area would be the height of the rectangle, top minus bottom, times dx. So that's done the same way that you find area, except you're multiplying by a density that could vary with x. So you might reasonably wonder, well, what if it varies with y, or with both x and y? The answer is that Math 175 methods are not up to that, but you do that in third semester, 275. So, you see, I'm trying to advertise third semester. I'm trying to encourage everybody to come back in the fall and take third semester. Okay, so what we call the moment in physics is like torque. It's a leverage length times the force, which is also what, say, if you have a wrench, you put the wrench on some fitting and you're trying to turn the bolt, what the force that is available to you is what you call torque, which is the length of the wrench times the force at right angles to the wrench handle. This is also what you call a moment. And so the moment in around a line to a differential mass is the distance from wherever your differential mass is to whatever the line is that you're measuring the moment around. So if you're, then what we're trying to get is the coordinates x bar and y bar of the center of mass. That's the balance point, like I was showing you with the homework papers and the pen. And as I said, it's on every line of symmetry if you have a geometric figure with uniform material. If you don't have uniform material, if your mass really varies with the x, you have a variable density, then you can't say that your balance point is necessarily on a line of geometric symmetry, because your material might become heavier as you move to the right, or it might become lighter. So now we go over to here, and what I was sort of trying to say is that moment and torque both mean a force times a leverage length. Then x bar is the lever length from the y-axis, and y bar is the lever length from the x-axis. So the x bar formula then is your integral, your leverage, you see. This, remember, is measured over from the y-axis. Your density, if it's variable and is a function of x so that our problems can handle it, our differential area. And we divide by our mass, which allows the variable density times the differential area.
What's that symbol in front of the X there?
What?
That one there, yeah.
Okay, there's an X there and there's not down there.
Oh yeah, the X in semicolon or parentheses, just to the right.
Okay, there's an X, and then this is the delta.
Okay.
This is the Greek letter delta of X. So it's X times delta of X times the parentheses.
Okay.
And in the Y bar, in the same way, the thing that you have to do is to write your lever length from the x-axis as a function of x, because these problems are set up to integrate with respect to x. So what we do is we use the average height of the representative rectangle for the lever length of each vertical slice measured from the x-axis to wherever this average point is. And so the y bar then is the integral, the density, and this would be the height of the rectangle. This times the dx would be the times the delta would give mass, and then the average to the center of the vertical rectangle from the x-axis is our average lever length. So you notice that what you have here is the difference and the sum of the two functions. So the product is the difference of squares. So this gives you the f square and this gives you the g square. Then I take the 2 out in front, and then I have the delta. And then I divide that by the mass, which is the same as it would be when you're doing x bar. You don't have to do 4 integrals, you only have to do 3. This one and the mass, which also works here, and then this one. So this works, you see, as long as your density could vary with x, because that's what your variable is of integration. If you had density that varied with x and y both, you would still have a problem because you'd have some y's in your formula here, and you don't have any connection between the y then and the x. So then you have to use the methods that you learn next semester in chapter 15. In the homework in 6.6, about half of the problems are just uniform material, and then you don't have to worry with the density at all, because if it's a uniform material, so that this is a constant, you see it'll factor here, and it'll factor here, and then it cancels. So if it's like the paper, it doesn't, as far as finding the balance point, it doesn't really matter what the density of the paper is. So when you have uniform material, as I've said a couple of times, your centroid, as it's called, lies on every line of geometric symmetry. So let's finish with problem 1 of 6.6. So your region is enclosed by the x square parabola from 0 up to 4, and it's uniform material. What they want is the center point of the area, really. And so you can see the y-axis is your line of symmetry. So that says x bar is 0. So you don't waste your time doing the integral. If you did the integral, it would come out to be 0, unless you made a mistake. Okay, so then thinking of this for the y-bar, you see the F is the top curve and the G is the bottom curve. I've labeled them here with the colors, and I've used the colors here. So what you're looking to get for this point, the y-coordinate, is first of all the mass. The mass would be the density, which you really don't have to worry about. And you're going from -2 to 2, and then you have top, which is y equal 4, minus bottom, which is y equals x squared. And your y bar then would be the half from the use of the average f plus g over 2 for this lever distance that I'm trying to indicate by tapping on the board. Just a second here. We have our density, we have our difference in squares over the mass. So here we have the half coming out, our density, our difference in squares, -2 to 2, and our mass, -2 to 2. Okay, you can take the deltas out and cancel. And the other thing you can do, we talked about this last week, if you have an even function, remember that's where the powers on the x are even numbers, including a constant, which is, after all, x to the 0 power. If you have an even function and you have limits from minus to plus, the same number, you can instead take a 2, which would be this 2, and change the limits to 0 to 2. It makes it easier to evaluate the definite integral if you're doing it by hand. Well, I have an even function here and I have down here. So both of them, I change the limits to 0 to 2, bring out a 2, which cancels. I brought out the constant delta that cancels. So I have a half of 16 minus x fourth to integrate from 0 to 2, divided by 0 to 2, 4 minus x squared. Okay, 16 integrates to 16x. This is x fifth over 5. Down here is 4x, x cubed over 3. So I put in the limits and go through the fractions, and I get 12 over 5, which is what the book says it is. Okay, don't go away. It's time for the first test, which you have a week to work on. You can take this home and bring it back either Thursday or Friday next week. I don't care between Thursday and Friday because I won't grade them until the weekend. And let me give one to everybody, and then let me have just a minute to talk about it. Except this sheet of paper. I want you to figure out how you're going to do the problem on some scratch paper, and then when you have the problem figured out, draw pictures and ask for, show your work and put in your answer. So I want you to, since you have time to work on it, I want you to present it. It's more than just work the problems. I want you to make it present it well so that it's easy to follow what your line of thought is and what you're saying the answer is. If you have to, you can write on the back. If you write on the back, then put an arrow on the edge of the problem so that I'll know to turn the paper and tell me, in other words. but I don't want anything except this sheet of paper. I don't want a lot of sheets of scratch paper. Okay? And you'll notice with problem 4 that it's very much like this one that we talked about in class last Friday, and where I gave you the maple handout, pointing out to you that you can either take the y positive down, or you can take the y negative down and take the absolute value. It's very much the same kind of thing, except that the radius is 26 instead of 5, and it's liquid chocolate, so it's a different density. But the other things, I think you can see pretty well that we've covered them. So if you'll come back tomorrow, then we'll continue from here on getting the centroids of various kinds of areas and curves and so on. So I'll see you tomorrow.